Okay, so today we're going to look at just solving polynomials, cubics, quartics, anything that's more difficult than a quadratic. The one that I have on the board, it happens to be a cubic, so I know off the bat that it should have 3 solutions. I have it equal to 0, which is convenient. If you think back to quadratics, we're always trying to get them to equal to 0 before we solve them. We've talked about why. I'll probably mention it again most likely in this video. But we're just going to walk through how I go about solving cubics, quartics, any polynomial that's higher than degree 2. So when you look at this one, the very first thing that I'm going to look for is ways to break this down and make it easier. Can I make it linear? Can I make it quadratic? Can I break it into parts that are easier for me to solve? So the very first thing I look for is simple factorings and or factoring tricks. Anything that helps me view it in an easier way. So what I noticed about this one is every single term actually has a factor of 2x. So what I can do is I'm going to go ahead and factor that 2x out. I'm going to rewrite this as 2x multiplied by the group x squared, subtract 4x, add 20, and I know this is all equal to 0. So this is nice because again, if you think back to quadratics, once I have 2 different pieces that are being multiplied, I know that one of these pieces, one of them has to be equal to 0. Because something times something equals 0, we know one of those somethings has to be 0. So at this point in time, I now know that either 2x equals 0, which is a linear equation, very easy to solve, which leads to x equals 0. Or I know that x squared minus 4x plus 20 equals 0. Which, this is quadratic. We have a lot of methods and ways that we can solve quadratic. My very favorite is factoring. It's just quick as long as we can use it. So when I look at this one, I'm looking for numbers that multiply and make 20 that happen to add to be -4. And I don't see any. I can't think of any quickly. I could try. But the second the second method that I go to, if that one's not working, is quadratic formula. So I'm going to go ahead and use that on this one. Thinking back to the quadratic formula, we know we're going to get x equals negative of a -4, so we're going to get positive 4 plus or minus the square root of -4 squared, which is 16. Subtract 4 multiplied by the 1 multiplied by our 20. And that's all going to be over 2 multiplied by the 1, which is really just 2. That 1 being that leading coefficient. So if I simplify this, notice what we get is we get that x equals 4 plus or minus the square root of -64, instantly making me think that I was happy. I'm happy that we went to the quadratic formula instead. I noticed I'm going to get complex solutions with an imaginary number in them. Factoring was not necessarily going to give me those, at least not conveniently. So now I just have to break down this root. We've had some experience breaking down roots. I could really rewrite this as the root of -1 multiplied by the root of 64. So root of -1, root of 64. So I'm really going to go ahead and rewrite this as 4 plus or minus. Root of 64 is 8, so I'm going to write this as 8. The root of -1 is I, so I have I all over 2. And then distributing that division to both terms, I'm really just going to end up rewriting this as 2 plus or minus 4i. So these happen to be my solutions that came from my quadratic. Notice we have 2 of them, 2 plus 4i, 2 minus 4i. So these are my values of x. Okay, I'm just going to put that on the end so we can see that. And then we also had x equals 0 as being another solution. And so there's my 1, 2, 3 solutions, which is what I expect from a cubic polynomial. Now if I wanted to, I could plug them back in, make sure that they actually do cause this thing to be equal to 0, cause this cubic polynomial to be equal to 0. I'm not going to go through that right now. The purpose is just to show the method. So, simple factoring tricks, break it down, make it more comfortable pieces, make them friendly equations, easier to work with, quadratics and linear, and then we solve from there. So this one was nice because there was a simple factoring trick to being able to solve this. I could just pull something out. Everything had something in common. Every term had that, factor of 2x in common. But this isn't always going to be the case. Sometimes, actually a lot of times, we're going to have a polynomial where there isn't a common factor in every term. It's not easy to factor right away. And so we have to rely on other methods. So let's go ahead and look at one of those. I've got one written down on a board for us. So x cubed multiply or subtract, 3x squared, add 16x, add 102. Now I'm going to go ahead and look for the zeros again. Keep in mind, if this wasn't set equal to 0, if I was looking for when this equals 50, I could always then subtract that 50, make it equal to 0, make it that friendly form again. But for the sake of solving, we're just going to look at this one really quick. So when I look, none of these really have anything in common. I don't see any kind of nice factoring tricks that I could use, at least not on this one. So, those options being like factoring by grouping, or notice that it kind of has a quadratic structure, things of that nature. I don't see any of that here. So I really need to do something different. I need to break this down into pieces, break these down into different groups that are multiplied. But I don't have a way to do that efficiently yet. So really what I need to do is I need to find one. I need to divide this, because if I can break it down, if I can pull out one linear term, I can figure out what's left. But that means I need to know what to divide it by. Now keep in mind our options here: synthetic division, we could use the rational root test. I could even try to factor this, maybe use a rectangular box structure. Everybody likes to use the box. So I could factor this. I've seen students do that. Some students are pretty successful with it. It takes me a little while to do that just with a cubic. It's a lot messier. So I'm not a big fan of that. I'm going to go for one of the other methods. So I need to go ahead and divide this out. I'm going to use synthetic division. Students seem to be happiest with synthetic division just because it leaves out the messiness of all the variables. So I'm going to go ahead and set that up. 1, -3, just using the coefficients, 16 and 102. And I know I need to divide it by something, so that's what I'm putting there. Keep in mind that if one of these terms actually didn't exist, you'd actually need to put a 0 in its place. Now I didn't know what to divide it by. I could use a calculator at this point in time to figure out one of the zeros, to figure out one of the solutions. I'm not going to do that. I'm going to instead use the rational root test. So the rational root test, really quickly, just going through that, I'm going to look at the leading coefficient, which happens to be 1. I'm going to look at that 102, which is our constant. And the rational root test says this: take your leading coefficient and take your constant and figure out all of the factors of them. So the factors of 1 are positive and negative 1, factors of 102, positive and negative 1, positive and negative 102, because those would multiply to make it. Positive and negative 2, I know that's because it's even. Positive and negative 51, half of that, because I used the 2. I also know that 3 is going to divide that, so positive and negative 3, and then positive and negative 34. Oh yeah, this one also has positive and negative 6, 6 and 17, so positive and negative 17. So a long list. Now, keep in mind the rational root test, if you remember back, it actually says that if we take any of these factors, any of the factors of the constant, and we put them over the factors of the leading coefficient, we could get a possible fractional root, a possible rational root to this, a possible solution. So I'm going to take any of these and I'm going to put them over top of those. Now it becomes nice: positive and negative 1 over positive and negative 1, positive and negative 1, positive and negative 102 over positive or negative 1, positive and negative 102. So really for mine, I'm going to have all of these as being the possibilities. Now, I want to find one of these that when I plug it in here will kind of work out. So let's just go ahead and pick one. I'm going to pick positive 2. Okay. Keep in mind, synthetic division, nice little process to it. Bring the first number down, 1, multiply, add, multiply, add, multiply. And I can see it's not going to work because I get 130 here. That really means I have a remainder. I should be able to decrease the degrees. Keep in mind this is a cubic because we have the cube term, the square term, the linear term, and then the constant. I'm still having all those, which means I tried to divide this out and it didn't divide out nicely if you think back to like long division and that sort of thing. So I need to try something different. I typically try numbers that are in the middle. I don't like to try the extremes first. The other thing that I'm noticing is When I got that positive in the end, it made that blow up, made it get bigger. So I'm thinking I'd like to use a negative, maybe eliminate some of those positives in the end there. Still want to keep something in the middle, so I'm going to try -3. If I do this, bring down that 1. So 1, multiply, -3, add, -6, multiply, 18, add, 34. Concerning me that it got big, but I get to multiply it by negative. That's nice. And that actually makes -102. So I get 0 there, which is exactly what I want. This means that -3 is a solution to this polynomial. It's a solution to that cubic. It also means that if x equals -3 is a solution, I could actually see a linear term or a linear factor of this as actually being x plus 3. Because -3 would have made that 0. And then, if you think back to like just dividing out numbers, I know that this will divide into that evenly, and this is the stuff that remained. Which means that if I multiply this, the x plus 3, the linear term that I divided out, multiplied by what I have left, I would theoretically get back to, actually, I would get back to what I had originally. So, I've now actually managed to factor it down. So this, linear term, multiplied by a quadratic. This is all the same thing as everything up there, and so I'm looking for where that equals 0. Now, we've already figured out one of those zeros. This is a quadratic. We can do the same thing we did for the polynomial that we looked at earlier. We can either try to factor it or use the quadratic formula. And you can go ahead and do that on your own. I basically just wanted to show you that we can take this cubic, we can break it down using synthetic division. You could use long division. Has a lot of benefits. I like it. Most people stick here first. We'll look at long division in a little bit. But we can break it down into a linear and quadratic. Two things that are easier to solve. And now I can look at when this is 0 or when this is 0, get my solutions, and I'm done. If you want to finish off this problem, go for it. I'll go ahead and give you the answers just in case you wanted them. If you actually solve this quadratic right there, when that equals 0, you will get x equals 3 plus or minus 5i. So we're going to get the two solutions from that. We've got the one solution from that one. And this is how you use synthetic division to solve a cubic polynomial. If this were a quartic, fourth power, quintic, fifth power, process is going to be the same. We're just going to have to go through more divisions to get it down to friendly pieces that we can solve in alternate ways. So this is how you can go about solving them by hand. Obviously you have other choices like technology. That's a big go-to, but it doesn't always lead to perfect answers. It misses a lot of times our complex solutions. And so being able to solve it by hand is really, really important. It's also important if you plan to be successful in college algebra course. So there it is. Hope you enjoyed. Good luck.